Hello, welcome to the Code Physics channel. Today, we want to continue with the topic of electronics, and today we are going to look at specifically a part known as transistors. So sit back, relax, and enjoy. A transistor, like a diode, is also made out of a semiconductor material. Okay? And it can be defined as a semiconductor device that is used to amplify or switch electronic signals. There are two broad categories of transistors, which are: number one, we have what we call the bipolar transistors, and number two, we have what we call the field effect transistors. Bipolar transistors use both of the charge carriers in the transfer of current or in the flow of current within the device. That means that both the holes and electrons are going to be used in the flow of electric current within the device, that is the transistor we're talking about. But when you talk of the FETs or the field effect transistors, they only need one charge carrier. That can either be the holes or it can be the electrons, but they need only one. We're only going to look at the bipolar transistors, not the FETs. Bipolar transistors can be divided into two. That is, number one, we have what we call the NPN transistor, and number two, we have what we call the PNP transistor. A bipolar transistor is made up of three parts. Number one, it is known as the emitter, and number two, we have what we call the base, and number three, we have what we call the collector. Now, this is a simple block diagram of our transistor, where we are having three regions, like we've said. Number one, we have the emitter, which is here. Number two, we have the base, which is in the middle. The base is always going to be in the middle. And then we have the collector on the other end. In other words, when you talk of a transistor, we have three parts, okay? Or we have three regions. The first one is going to be the emitter, the second is going to be the base, and the third one is going to be the collector. Now, the emitter is very rich in current carriers. In other words, this one, it is doped more with current carriers than the base and the collector. Okay? Now, its major function is to send these charge carriers to the collector, or it is to send these current carriers to the collector. But before these current carriers reach the collector, they must pass through the base. So the base is going to be acting as the control region. It's going to be determining how many current carriers are going to flow to the collector from the emitter. Now, let us first of all look at the NPN transistor. In the NPN transistor, the diagram, we have it here, okay? We have one region that is doped with electrons. That is the meaning of N. Remember that N represents the electrons. And then the middle region is doped with holes. That is the P. P representing holes. And we have another region, N region, that is doped with electrons. Now, the first region, the emitter, is doped with the electrons. Okay? But here, the doping is very high. Okay? And then, even here, the last one, which is going to be the collector, is also going to be doped with electrons. But the doping in the emitter region is not the same as the doping in the collector region. Doping is much more in the emitter region than in the collector region. Well, the middle part, that is going to be the base, is doped with holes. So when you talk of an NPN transistor, this is one where the emitter is doped with electrons, the base is doped with holes, and the collector is doped with electrons. Now, in this kind of a transistor, the majority charge carriers are going to be the electrons. The middle region, that is going to be the base, its doping is going to be very light. Okay? The holes that are doped in the base region, the number is going to be very minimal. as compared to the emitter and as compared to the collector. So the base region is lightly doped, okay, whereas the emitter region is immensely doped, and also the collector region is immensely doped. But the doping of the collector region is slightly less than the doping of the emitter. Also here we have to understand that we have two p-n junctions, because in the middle we have a p-type region, and then it is connected to the down part, which is the n-type region, meaning that there is a boundary between the p-type and the n-type on the side of the emitter. Then also here we have the n-type region. Again, it is connected to the p-type region. So because there is a connection between the collector and the base, there is a p-n junction that is going to be connected in between. Therefore, this means that we are going to be having two p-n junctions. Now this is our symbol for the NPN transistor. In other words, this is the symbol that represents NPN transistor. So we have our three parts, like we said. We have the base, okay, we have the emitter, and we have the collector. Now here we find that the arrow, there is an arrow which we've drawn here, okay, and this arrow is facing towards the emitter. It is moving towards the emitter, and this is how we are going to differentiate it from a PNP transistor. A PNP transistor, again, is having three parts, or it is having three layers, or it is having three regions. This is the block diagram we have, and we have the first block representing the emitter, and it is doped with holes. Remember that P represents holes. And then the middle region is going to be doped with electrons, and the upper region, which is the collector in this case, is going to be doped with holes again. And in this kind of a transistor, the majority charge carriers are going to be holes. It also has two PN junctions, as we saw for the first case, that is the NPN. Now in all cases, it is going to happen that the base region is always going to be lightly doped as compared to the emitter region and the collector region for a transistor. Now this is the symbol for PNP transistor. Okay, we have the base like we had for the NPN, we have the collector up here, and then we have the emitter. Now the only difference, like I said before, for the NPN transistor is going to be in terms of the arrow. You observe that here the arrow is moving away from the emitter, okay, whereas when you talk of NPN transistor, the arrow is moving towards the emitter, okay. So this is how we can differentiate them. In the NPN transistor, the emitter base junction is always forward biased, and also the base collector junction is reverse biased. This is always going to be the connection for a transistor, whether it is NPN transistor or it is PNP transistor. That is, once again, the base emitter junction is forward biased and the collector base junction is reverse biased. Therefore, as we connect, our batteries are going to be connected. As we can see here, the NP, that is the emitter and the base, the emitter is connected to the negative of the battery, whereas the base is connected to the positive of the battery. Then the base collector region is reverse biased. This means that the positive terminal of the battery is going to be connected to the inside, which is going to be, in this case, the collector region, whereas the negative terminal is connected to the base region. Now the emitter base junction is forward biased, meaning that the negative of the battery is connected to the n-type side, that is the emitter region, and the positive terminal of the battery is connected to the base region. That's going to happen is that because this is forward biased, that is the emitter base junction is forward biased, then the electrons that are found in the emitter region are going to be repelled by the negative terminal of the battery, meaning that these electrons in the emitter region are going to be pushed towards the PN junction. Okay? Now, when they're pushed towards the PN junction, they cross over, they enter the base region. Now, when they enter into the base region, they're going to find there are few holes. So a few of these electrons that have entered the base region recombined with the holes that are found in the base region, but the majority are going to cross over onto the collector region. Why? Because of the positive potential of the battery that is connected to the base collector region. So this positive terminal is going to attract electrons. Therefore, you find that most of the electrons are going to cross over the base region into the collector region. How does a PNP transistor works? We have seen how NPN transistor works. Now let us see how the PNP transistor works. Again, the connection is going to be the same. That is, the base emitter junction is going to be forward biased, whereas the base collector junction is going to be reverse biased. So in this case, this means that the positive of the battery, okay, is going to be connected to the P type side. It's going to be connected to the emitter. But remember now, the emitter is having holes as the majority charge carriers. Then the negative of the battery, the first battery, that is for the base emitter junction, is going to be connected to the base region. Okay? Then the base collector junction is going to be reverse biased. That means that the positive of the battery, of the second battery here we have, is going to be connected to the base region, while the negative terminal of the battery is going to be connected to the collector region. What's going to happen is that the positive of the battery is going to repel the holes that are found in the emitter region. Now, when they repel, they are pushed towards the PN junction, and most of them are going to cross over onto the base region. Now, when they enter the base region, they are going to meet electrons. Some of them are going to recombine with the electrons that are found in the base region. But remember that the base is always lightly doped. In other words, it is having very few charge carriers. In this case, it's going to be having very few electrons. So this implies that a few of these holes, when they enter the base region, they're going to recombine with the electrons. They're going to be filled with the electrons that are found in the base region. But a majority are going to cross over onto the collector region. This is because there is a negative potential here of the battery, of the second battery, okay, which is going to be attracting these holes. So we find that most of the holes are going to cross over into the collector region, while a few are going to recombine with the electrons that are found in the base region.